All right, how's it going, everybody? I am recording this video here on Friday, April 9th, and today we're going to look at our section 9.2, polar equations and graphs. In our previous video, we introduced the polar coordinates and the polar plane. And what we kind of saw at the very end of that video is that it can be kind of tricky to graph polar equations. So we're going to talk more about converting equations in and out of polar and identifying some of the graphical features. At the end, we'll look at some general shapes that often arise when we're graphing things, in polar form. And I'll generalize a couple of those shapes, and I'll have you generalize a couple of those shapes for your homework out there as well. So what we're going to do is we're going to look at these in order of difficulty, because some of these can get kind of tough to handle here. The easy ones, the first grouping, the ones that you're seeing on the screen right now, these are the ones that I expect all of you to just straight up know, that if you see it in the future, you can say, oh, I know how to graph that for sure, and just do it right on the spot. Then we're going to see some medium ones where if we do a little bit of work, we can figure out what the graph should look like, but it takes some effort. Then we're going to see some harder ones where we certainly still can graph them, but it starts to take kind of a lot of effort. And what I'm a little bit more interested in is our ability to understand why graphs might have those shapes and be able to generalize general forms of equations, rather than me saying graph this function and you having to plot 26 different points to be able to produce a good graph kind of thing. I'm not super interested in that. So we'll see that once we get to the harder ones, which are really the more interesting ones, the focus is going to kind of shift a little bit right there. So let's go ahead and look at these easy ones. And again, I kind of want to say, I try not to say that something's easy or hard. I try to put that in quotation marks as more of a comparative statement there. Not trying to make anybody feel bad, but these are the ones where I definitely expect by the end of this unit with polar things right here, that these are in a sense automatic for you to be able to produce these types of graphs right here. For all these, we're going to want to do a smidge of algebra to sort of justify the math that we're doing. But let's go ahead and see what that's going to look like here. So for our very first graph that we're looking at here is the graph of r equals 3. What this says to me is I would like to graph the set of all points that have a radius of 3, that's a distance of 3 from the origin, and it appears that there is no restriction on angle. So how do we graph the set of all points that are 3 units away from the origin? Well, this should just be a circle, right? Should be a circle of radius 3. Excuse me. Right? The radius is 3. It's a circle of radius 3. It's all points that are 3 units away from the origin. Now, there is a little bit more that I kind of want to say about this right here. We know that we've got the conversion. R is the square root of x squared plus y squared, right? That was one of our polar conversion equations that we came up with last time. So it seems like we should be getting the square root of x squared plus y squared equals 3. And if I squared both sides, I'd get x squared plus y squared equals 3 squared, or r squared. This is the general form of a circle. All right, I want to modify that statement ever so slightly. So the important generalization I want to make here is that x squared plus y squared equals r squared, radius squared, is the general form of a circle if that circle is centered at 0, 0. What if our circle is not centered at 0, 0? Well, in general, we can also generalize this by saying x minus h squared plus y minus k squared equals r squared is the general form of a circle centered at h comma k. And importantly, notice that these minus signs are built into this formula. So like x minus 2 would say that positive 2 is the x component of the center of that circle of radius r. That's right there. This will come up again in some later problems here, but this was just saying graph r equals 3, and I kind of went off on a little bit of a tangent with the x and y stuff right here, but this is going to come up here in a little bit, so we'll care about knowing that this is our general form of a circle right here in a little bit. So next graph right here, theta equals pi fourths. What this is saying to me is I am interested in drawing the graph of all of the points that in a polar graph have an angle of pi fourths. It seems that there's no restriction whatsoever on radius, so we can be any distance that we want from the origin as long as the angle that we make with the positive x-axis is pi fourths. So what is this graph going to look like? Well, I just want to find all points that make an angle of pi fourths with the positive x-axis. So that just seems like it's going to be, all right, that didn't work out quite as nicely as I wanted to right there. It should just be basically our pi fourths line, right? I mean, there's our 45-degree angle right there, and it should be able to go in either direction. Remember that we said that our radius could be negative, which is a little bit awkward, but this is our positive radius, and theta being pi fourths line. This is our negative radius, and theta being pi fourths line right here. These are all of the points that have an angle of pi fourths relative to the x-axis right here. This is the same as the line y equals x. Now that's interesting a little bit because with y equals x, I actually know a way to do some math with this guy. I wish I could write this underneath, but I can't. Because y I know is r sine theta, and x I know is r cos theta. I can divide both sides by r. I can divide both sides by cosine and get sine theta over cosine theta equals 1. Well, that's really tangent theta being equal to 1. And this is saying, what are the solutions to this? Well, the solutions to this are pi fourths, that's this angle, and then 5 pi fourths, right? This angle that's sitting down here, that's in our third quadrant with negative x's and negative y's. And so that's exactly what we're seeing right here, is this is our pi fourths, and this is our 5 pi fourths down here. Or this is our pi fourths with positive radius, this is our pi fourths with negative radius right there. But in any event, this saying that is the same as the line y equals x, we can make that agree with the trig that we've been doing here as well. So that's sort of like our double verification that we did this correctly right there. So what's up with these other two easy graphs? These ones don't look as easy, except I recognize that r cos theta is exactly one of our conversion factors from the previous section. So that looks to me like this is literally just x equals 2, because x equals r cos theta. That's exactly our conversion between polar and Cartesian. So it seems like this is just the graph of x equals 2 right there, where we're at 2. That's not that crazy. Similarly over here, r sine theta is y. So this should be the graph of y equals negative 3. And I can graph the line of all points that have a height of negative 3. It's right there. There's my graph of y equals negative 3 on that guy. These are our 4 graphs that I think are the ones that you should be able to do very, very, very easily. And you should notice that these 4 graphs represent each of our 4 different variables that we discussed, x, y, r, theta, all being equal to a constant number. Radius is constant, gives us a circle. Angle being constant gives us a straight line through the origin with that angle relative to the positive x-axis. X being equal to a constant is a line where all the x values are the same. Y being equal to a constant is a line where all the y values are the same right here. So this is really just 4 equations in polar form, but where if we convert these 2 equations into rectangular, we recognize that this makes 4 equations that are just a variable equal to a constant. And that's why these are the easy ones. I do think these are pretty easy. So these are the ones that I expect if I were to walk up to on the street and say, quick, graph theta equals pi sixths, that you could do it on a napkin in 20 seconds, because it's not really that hard to do that, right? It's just all the points that have this given angle in polar form. Okay, got it. So these are kind of our baseline basic graphs right here. Now let's go ahead and look at the ones that might take us a little bit more work for us to end up coming up with their appropriate equations. And you should notice that these ones immediately feel like this guy up here, but the difference is that here the r is multiplying the sign, and here the r is on the other side of the equal sign. So not quite really the same. So let's go ahead and attempt to graph these. And the way that we're going to attempt to graph these is by converting into our rectangular coordinates to see if we can get a little bit better of an identification of what we're looking at here. So what I kind of know, what I'm thinking to myself over here, is I'm remembering my list of all of my conversions that I know that you guys are never going to forget for your entire life, which is that x equals r cos theta, y equals r sine theta, r equals square root of x squared plus y squared, and theta equals tangent inverse of y over x. Right, those are our essential conversions right there. So what I'm thinking to myself is, if I think that I want to try and get graphical information by converting these into rectangular, then what I need to do is I need to build either. I need to build statements that look like r and theta so that they can get into x and y, or I need to build statements that look like r cos theta and r sine theta to get those converted into x and y. In both these cases here, the math for these is going to be very, very similar. And you can see that in this case right here, we're kind of close in both departments right there. And by the way, I feel like I should state that I typically write this one here. This one is very often written as r squared equals x squared plus y squared. I think it's actually a little bit more typical to state it that way. We just like to directly solve for r sometimes. So the point is this. I feel like I almost see r squared over here, but it's just an r. I feel like I almost see an r sine theta over here, but it's just a sine theta. In both cases, they're both missing an r factor that I kind of wish that they had. So what I think my good algebra move here is going to be is to multiply both sides by r. This is going to give me r squared equals 4r sine theta. Now, notice here that I did a slightly unnatural thing, which is I multiplied a product of two numbers by a third number, and I jammed that third number in between the 4 and the sine. That's because the whole reason I was multiplying by r is because I wanted to see stuff that looked like this. So I'm writing it in the order that I think I want to use it. Now, it seems to me like r squared I can rewrite as x squared plus y squared. It seems like 4 r sine theta I can write as just 4y. So what this feels like I'm getting close to is it feels like I'm getting close to something that looks like one of these general forms of a circle. But what I can see is I have some leftover y components right here that I feel like I need to deal with. So this sort of says to me, I think that what we're going to get is something that's sort of like halfway between our form of a circle at 0, 0 and our form of a circle at hk right there. Because it doesn't seem like there's anything that's wrong with our x stuff right here. I just have x squared. But it seems like the y stuff I need to rewrite a little bit differently here. To give ourselves a little bit of help here, I want to remind us what happens when we square out a binomial term here. I think I'll just allow myself some of this space right here. Just thinking about where to put this here. So what I'm going to do here is I'm always going to group all my terms over onto one side. Do x squared plus y squared minus 4y equals 0. And what I'm thinking to myself is I want to rewrite y terms, y squared minus 4y, as a squared binomial. Something like y minus, I don't know, a squared. So it fits the general form of a circle. Okay, so if I'm referencing that this is the general form of a circle, then I certainly should just write this as y minus k squared, so it actually looks like that, right? Here's our general form of a circle right there. There's that y minus k squared. That's what I want this to look like. So what does it look like when I've got these binomials squared like this? Well, I can just do a couple of these, right? If I did y minus 1 squared, this is really the same thing as y minus 1 times y minus 1. If I do y minus 1 times y minus 1, what we're going to find that we're going to get is like a y squared for the first term. I'm going to get negative 1 times y once, and then I'm going to get y times negative 1 a second time, so I'm really going to get a minus 2y. And then in the end, I'm going to get negative 1 times negative 1, which is a positive 1. If I tried another one of these, y minus 2 squared, if I square the first term, y times y is y squared. When I think of this as y minus 2 times y minus 2, I'm going to realize I'm going to get a y times negative 2 and a negative 2 times y. In total, that's going to give me negative 4y. And hey, doesn't that feel like what we have? If I were to keep going with some more of these out here, y minus 3 squared. Well, y times y is going to give me y squared. And again, picturing this as y minus 3 times y minus 3, I can see that I'm going to get a y times negative 3 and a negative 3 times y. So that's a total of negative 6y in the middle. And on the end, negative 3 times negative 3 is a positive 9. right? And this list kind of keeps going. What this list is trying to help us do is recognize that if we have some form of y minus capital A squared, now is an appropriate place to use it. I'm going to get y squared for my first term. I'm going to get y times negative a and negative a times y for a minus 2ay, and I'm going to get a plus a squared out there on the end. And this general form right here is going to help us see how we can write our general quadratics as these squared binomial ones that are actually the terms that crop up in our general form of a circle. So what do I want to do right here? I've got x squared plus y squared minus 4y equals 0. What it seems to me like I want is I could write this as y minus 2 quantity squared if I had a plus 4 out here. That plus 4 is really the thing that's missing to make that all work out for me. So I'm just going to bring it in. Plus 4 is going to sit right there. And I'm going to say that's equal to another 4 on the other side. I've said, listen, this y squared minus 4y is almost a good term. If there was also a plus 4, I could make it an excellent term that I want it to be. But if I add 4 on the left, I got to add 4 on the right. That's just what I'm going to do to make sure that this grouping right here works out to be the nicest possible grouping for me here. All right, so now this y squared minus 4y equals 4 is exactly this y squared minus 4y equals 4 that you're seeing, or plus 4 that you're seeing over there. And therefore, I can go ahead and write this guy as x squared plus y minus 2 squared equals 4. And therefore, I'm noticing that this really looks like x minus 0 squared plus y minus 2 squared equals 2 squared. So this is a circle of radius 2 centered at 0, 2. Because our general form up here, we said x minus the h and y minus the k. Whatever h and k are where we're centered at. Notice that these negatives are built into the formula right there. So if I have like y minus 2, that means that positive 2 is the y value that we're interested in for the center of the circle. So I can see here, x we didn't move at all. Y got shifted up by 2 units because 2 is going to get taken away from us, so we need to contribute 2 more than we used to have to. And so this guy will be a circle of radius 2 centered at 0, 2. And so centered at 0, 2 with a radius of 2, so therefore it must be sitting directly on the x-axis right there. All right, so we did all the work for this one. I'm kind of wondering. Now let's see that this second example right here is going to follow the exact same pattern. So what I would highly recommend right now is, now that you've seen our route to the solution for this guy, you should pause the video and you should attempt this guy right here. See if you can convert this into rectangular, and then see if you can determine the appropriate way to complete the square to get into our general form of a circle, and then state the 2 features of the circle. Where is it centered? What is its radius? And draw a little picture of it. So pause the video and attempt to do that now for this one here. It's going to be very, very similar to the one that we just did. Okay, great. Now that you're unpaused, and I'm confident that you all stopped for a moment and actually attempted this problem on your own, I'm going to follow some very similar math. As with the previous one, I'd like to see my cosine have an r in front of it so that I can convert it into x. I really like to see my r not as a standalone term, but as an r squared, because then I don't have the square root to deal with. So I'm going to go ahead and multiply by r. R squared equals negative 2r cosine theta. R squared I'm going to rewrite as x squared plus y squared equals negative 2x. I'm going to move all my terms over to one side. X squared plus 2x plus y squared equals 0. And again, I'm trying to get my x stuff together here. So I don't want to just add 2x and put it to the right of the y squared. Like, I'm trying to like deal with my x's, just like over here I was trying to deal with my y's, right? So I'm going to go ask myself, what can I do to introduce a new term to get those x's to, just like we're saying over here, I don't want an x squared plus or minus some quantity of x. I want x plus or minus a number quantity squared, because then it will look like my general form of a circle. So I'm noticing here that this expression right here looks almost like the terms that I have right here. The difference is that this has a minus sign right here, but that's also because it has a minus sign right here. So I'm thinking to myself, I feel like I should be able to do some form of x squared plus 2x and I'm going to do a plus 1. Because that's going to give me the perfect terms that I need to be able to rewrite this as that is now a perfect square trinomial. And that's also going to give me the 1 on the other side over here. Now I can go ahead and say, listen, these three terms right here, that's what you would get out if you squared x plus 1. So now we've gotten ourselves into the general form of a circle in rectangular coordinates. This is the general form of a circle with radius 1. The 1 is because the square root of 1 is 1. Centered at. Now, where's this thing centered? Be careful with this one. It's super easy to make a small mistake. Our general form says that x minus h squared says the x value of the center is at h. I have x plus 1. So we should really be thinking of this as, I'm just going to write my comment down here. Okay, that was a stupid place for me to put that comment. Let me put it in the center where I've got my comment room right here. X plus 1 squared is really like x minus negative 1 squared. So it seems to me like this is our x minus h squared, right? So it looks to me like h is negative 1. So it seems like where we are centered is at negative 1, 0, because we didn't make any adjustments to the y term right there. So it seems to me like this should be a circle that's sitting here centered at negative 1, 0. And therefore that location right there is an x value is like 2, because the radius, it's going to go one radius from right to left middle, and then one radius from middle to left right there to get us out to 2. So let's go ahead and double check in Desmos that we're not crazy, that we got these graphs correct right here. R equals 4 sine theta, r equals negative 2 cosine theta, and we should be getting a circle of radius 2 sitting on the x-axis on top. We should be getting a circle of radius 1 sitting to the left of the y-axis right here. So let's go ahead and check these guys out. Okay, so I am looking at here for my graphs. I am interested in seeing r equals 4 sine theta. And there it is, just like we had anticipated, sitting on the x-axis with 0, 2 being the center of the circle. The other one that we were interested in graphing was r equals negative 2 cosine theta. And we can see, once again, we were correct right here. We did get this circle of radius 1 because it's centered at negative 1, 0, and it has a radius of 1. It goes 1 unit to get to all of its points that are out there. So maybe I can go ahead and grab a little, come on, give me that count. Oh, I see what I need to do. Let me get my minor grid lines out of here and make sure that the step size is 1 for each of those things. Okay, and let me go ahead and snag a little snip of this guy here. Go throw this guy out my notes here. All right, so there's my 2 final graphs right there. All right, so now I got these graphs thrown in here in Desmos as well, so we can verify that these two things collectively on one graph right there looks all good. So sometimes we got to do a little bit of algebra right here, and this algebra, I mean, completing the square is not a trivial thing to do right there, right? These are some of the easy cases right here. These can get certainly more complicated, but you guys can see that sometimes it helps to work towards this rectangular coordinate version of the general form of a circle, knowing that we want to have all of our x stuff squared and then all of our y stuff squared. Will help us understand where the center of the circle is. The r squared on the other side will help us know where the radius is. And remember that it's always r squared. So for our two equations, the fact that this was 4 really meant that the square root of 4 is 2, so that was the radius. Here, the reason we got 1 for the radius isn't because that number is 1. It's because the square root of 1 happens to also be 1. So that was really r squared right there, but that just left us at 1, since square rooting 1 doesn't really do anything. So there we go. So we've done our easy ones. We've done some of the harder ones that require some real algebra techniques to make happen here. Let's go ahead and look at the harder ones where we can't just do some algebra and be like, oh, I know that shape. Like these were still just circles, right? We're going to get a lot of shapes we don't necessarily recognize. So here's the deal, the hard ones. When the equations get a bit tougher to graph, it gets helpful to identify any symmetry that our graph might have first to help us out. Here are the three symmetries that we should go and we should look for here. So our first symmetry is going to say this. Suppose you replace all of the thetas in your equation with negative theta. If when you then simplify your equation, you get the exact same equation back, if that negative didn't make any difference to your actual equation's evaluation, then there should be some symmetry we've identified, and we kind of know how this works, right? We've seen this graph before. If we start with some angle of theta here, we could instead look at negative theta, and what did these 2 points have in common with one another? Well, these 2 points are clearly symmetric over the x-axis. If we replace theta with negative theta, and it gives no difference. All right, that's one type of symmetry we could hunt for that's out there. What else? Well, another way that so this one gave a symmetry over the x-axis, right? A mirror image over the x-axis. If we instead replace theta with pi minus theta, then what kind of symmetry is this going to give us? Well, again, I can start with just some generic angle right there. There's theta. If I instead wanted to graph pi minus theta, what would that look like? Well, this was 0 plus theta. So pi minus theta would say, start at pi radians over here and subtract off the same amount of angle as we rotated through over here. So that's going to tell me, that's going to take me to this guy right here. Here's my pi minus theta right there. And so we can see that these 2 points are always going to be left-right symmetric, symmetric over the y-axis. If we replace theta with pi minus theta and find no difference. Finally, another type of symmetry that we could see is what happens if we replace r with negative r. If we replace r with negative r and it doesn't actually change our equation, for example, if the only r in your equation was actually an r squared, then replacing r with negative r, positive r squared is the same thing as negative r squared. So that would be no change in our actual original equation. Now, what I can kind of visualize for myself here is suppose we had some point here that has some given r value, then it might be the case that we would negate the r value and we'd be sitting down here instead. So what you should notice is that this is always going to be sort of symmetry over the axis, which really is going to be the same thing as like a rotational symmetry here. I am going to call this odd symmetry since this is really what a math person would call it right here. We haven't been using those words of odd or even as much this semester. Rotation by pi radians or 180 degrees symmetry. If we replace r with negative r and get no difference, right? And so all this, when I say and get no difference, what I mean is if we could have changed r to negative r in the equation, but the equation actually evaluates the exact same, if you just simplify it and you get back the original equation with no differences in it, then we have that symmetry, right? Now, here's going to be the little bit of a bummer about these symmetry checks. Somewhat unfortunately, if you check for a certain symmetry, if I swap out theta for negative theta and find that my equation is the exact same after a little bit of simplification, then that means that I definitely do have this symmetry over the x-axis. And therefore I know if I can graph the top half, then the bottom half is going to match identically. Unfortunately, if you fail a symmetry test, you actually still might have that symmetry, and I'm going to show you in Desmos why that might end up happening. So the unfortunate thing about these symmetry tests is that they're not yes, no. These symmetry tests are yes, maybe. Which is unfortunate here a little bit. So let's go ahead and do an example here, and I'm going to show you kind of this whole you know, this is an example of mostly this pass-fail business right here. So let's go ahead and check this thing for our three types of symmetry that we have right here. Um, and see what we end up seeing here. So our three symmetry tests, our first symmetry test says swap out theta for negative theta and simplify. So what that's going to give me is r equals sine of 2 times negative theta, which is r equals sine of negative 2 theta. And what we know about our sine symmetries, this is back to chapter 6 topics right here, is that when you take the sine of negative of an angle, you're going to get the negative of the sine of when you got the positive of the angle. And I can see it in this picture right here. You should know that the sine value, like sine, of this top angle is the same number as for the bottom angle, but since we're measuring height, the bottom one's going to be a negative height and the top one's going to be a positive height. So I know that this is r equals negative sine of 2 theta. And so I see here it's not the same. It's not the same as the original equation. So this says to me, I don't know. I don't necessarily think that I have that symmetry over the x-axis right there. We failed that symmetry test. But as we know, if we fail a symmetry test, we might actually still have that symmetry. Our next symmetry to check for is what happens when we replace theta with pi minus theta. Well, I can go ahead and make that substitution here. I'm going to I just obviously need more room right here, dang it. I'm going to go ahead and do my r equals sine of 2 times pi minus theta. I'm going to write this instead as r equals sine. I'm going to multiply out in the middle, 2 pi minus 2 theta. And I don't quite know, well, I guess I do know what to make of this guy right here. This should be, I'm actually thinking of this as like r equals sine of negative 2 theta plus 2 pi. And what I know is that if you add 2 pi inside of a sine function, that doesn't do anything. This is coterminal with negative 2 pi, right? So this should just be sine of negative 2 theta because of the periodicity of the sine function by 2 pi. And now we're right back into the same scenario we were in a second ago, where we're getting r equals negative sine of 2 theta. And so it's not the same as the original because our original doesn't have this negative sign sitting out front. I just don't know why I thought I was going to be able to fit that example in that amount of room right here. Finally, let's go and look at our last one. This will be the easiest check to do. Replace r with negative r to see if we get radial or rotational symmetry. So therefore, negative r equals sine of 2 theta. Well, there's no simplification to do. I don't have like math to show for this guy right here. I guess a thing I could do is I could rewrite this as r equals negative sine of 2 theta. And again, it's not the same as the original. So what I'm going to say here is, in this case, we failed all three symmetry tests. But we know we still might have those symmetries. Let's check a graph. So my question is, what symmetries does this graph actually end up having? So pop over to Desmos and check this guy out. R equals sine of 2 theta. We failed all three of our symmetry tests. Let's see, does this thing have symmetry? Well, it looks like this is a super symmetric graph, right? What I'm seeing here is it looks like we do have symmetry over the x-axis. We do have symmetry over the y-axis, and if I were to grab this graph and rotate it by 180 degrees, it lands back on itself again. So it seems like we got all three rotational symmetries with this guy. Or sorry, we got all three symmetries, the x-axis, the y-axis, and rotational symmetry for this graph right here. So that's slightly disappointing for this whole symmetry test thing, that we can always do these symmetry tests, and sometimes we get symmetry even though the test did not inform us that we did. I want to show you briefly why this happens sometimes. This is just a little unfortunate. So why did we fail the tests, but we have the symmetry, all right? So I'm bringing this back into my Microsoft Word and saying, okay, we actually have all three types of symmetry: x-axis, y-axis, rotational. We got them all, right? So let's take a quick look as to why this is happening here. And to help us see it, what I'm going to do is I'm going to change the angles through which we're considering right here. So what if I only looked, instead of, so it started out going out to 2 pi to get the whole thing, right? So let's just see what this looks like chunk by chunk. So if I do pi halves, which is just 1/4 of it, I get this part that's right here, right? Now what happens if I go to pi? Well, you should notice that the second chunk that got swooped out was the second component of this guy right here. So the deal that's happening here is that when we swap out positive, so let me do it this way right here. Let me do pi halves, and you should notice that we could have swapped this out. So from 0 to pi halves gave us the upper lobe. One of our symmetry tests was to check and see what happens when we swap this out for negative pi halves instead. So make our theta be the negative instead. So if I did negative pi halves to pi halves, then you should see that this didn't actually give us top-bottom symmetry like we expected. That's actually what gave us the left-right symmetry in this case right here. That's a little bit unfortunate. The other thing that I could have done is starting from 0 and going out to like our 2 pi instead, I could have replaced theta with theta minus pi. So in this case then, that would be like me doing from negative pi to just pi right here. But the thing that's going to happen, I can't. So what I wish I could do in here is I wish that I could make this like a variable so it would like draw the curve so that you could see in what order these things are getting drawn. I guess the thing that I want to say here is that when we go from 0 to pi halves, it gives us that lobe there. But then when we go from pi halves to 2 pi halves, it's giving us the bottom lobe that's down there. So these were supposed to be showing us, I guess, to go for our 3 pi halves. So what's happening here is that these lobes aren't matching up with one another left to right or top to bottom. They're actually matching up with each other more diagonally when we go from 0 to pi minus, or theta to pi minus theta. And so it's not seeing that the other component is there because they're matching up diagonally instead. But that when we get both the symmetries, that we have that all that symmetry going on. So the point is here, these can be a little bit tricky as to in what order the loops get swooped out in will affect whether or not we're able to actually detect them. If it swoops them out 1, 2, 3, 4, then that will be different in our detection ability for the symmetry than if it does something like 1, 2, 3, 4, or something like that. So the point is, these can be kind of tricky. You should absolutely be playing around with these bounds when you graph these things to see which lobes or petals are swooped out over which intervals out there. And those might be some questions that I might also want to ask, which is saying, graph this function only over some given interval. Or for me to say, I want to graph this function, but I only want to graph the components that are in the third quadrant. What interval of theta values should I do to get the third quadrant values? And you can just kind of play around with them out there and see what you're going to get with those guys. So playing around with those bounds, really meaningful, important thing. You got to make friends with Desmos for this section, or else you're going to have to do a mountain of by hand work that I don't want you to do. So be friends with Desmos. All right. So let's come back over here to Microsoft Word and let's look at some more examples. So let's see if we can graph this good one right here by hand, and then we'll do all the hard work for this guy one time right here. So let's go ahead and check this guy for symmetry, and then let's see if we can actually just graph this by hand instead of running to Desmos for help. So let's do our 3 symmetry checks here. So our 3 symmetry checks are theta being swapped out for negative theta, theta being swapped out for pi minus theta, and r being swapped out for negative r. All right. So let's check these three symmetry checks right here. So this should give me r equals 1 minus sine of negative theta. That's going to give me r equals 1 plus sine of theta. Not the same. For our next check over here, I'm swapping out theta with pi minus theta. R equals 1 minus sine of pi minus theta. I'd like us to return to our diagram here for a moment. When we talked about this one, here's our theta and our pi minus theta. What you can see is in our previous one that we just did, we got a positive sine value versus a negative sine value, and that's why they were different. But over here, theta and pi minus theta, they both have the same sign when we apply the sine function, right? They're both the same positive number. These two have different cosines right here, but they have the exact same sine of theta and sine of pi minus theta are exactly equal to one another. So I can tell here that I am, in fact, going to just get 1 minus sine of theta, and therefore they are the same. So we definitely have now, which symmetry was it that we just decided that we have? Well, the reason that I can remember it is because theta and pi minus theta are always reflections over the y-axis. So we're symmetric over the y-axis. So we have left-right symmetry. Finally, let's check if we swap r for negative r, we get it. I hope that you can pretty much see by visual inspection that there's no way. This one really only happens if you have squared r values pretty typically, and I don't see a square on my r value here. So just no. I'm going to say this is equal to negative 1 plus sine of theta. Not the same. So we did at least get one positive test here. And what that tells me is I expect the left and the right halves of my graph to be identical. Maybe the top bottom, but not necessarily. Maybe rotational symmetry, but not necessarily. So let's go ahead and take a look at doing the legwork for graphing this guy. I'm only going to make you do this once right now and probably once on the test, but that's okay. So let's go ahead and try and plot some easy points. So here's maybe a question I might have. Plotting some easy points. Here's a thing I'm thinking. Sine of theta ranges from negative 1 to positive 1. Therefore, r equals 1 minus sine theta. I'm thinking that sine of theta gets as small as negative 1 occasionally. 1 minus negative 1 would give me 2. Alternatively, sine theta gets as large as positive 1, and 1 minus 1 gives me 0. Also, I know that sine theta is occasionally 0, and 1 minus 0 is just 1. So what I want to know is, when do we get to those radii? Wow, that was, I wrote like the wrong letter every other letter right there and just kept on writing. It technically worked out. What angles result in these radii? I want to know, when do we get to r equals 0? When do we get to r equals 1? When do we get to r equals 2? And I'm picking those smartly because I know what values sine ranges across, right? So I'm thinking to myself, r equals 0 says to me 1 minus sine theta equals 0. So sine theta equals 1. You guys know that sine gets to a height of 1. only at theta being equal to pi halves. So I now know that, and I'm thinking to myself, I want to graph my r theta pairs. I'm just going to come up with a list of points out here. R equals 0, theta being pi halves, that's one ordered pair. I know that if r is 1, then we're going to get 1 minus sine theta is equal to 1. Therefore, negative sine theta equals 0, or just sine theta equals 0. And we know that sine theta equals 0 at 0 radians and at pi radians. So I actually got two points out of this one. Notice there's two ordered pairs here. I got 1 with 0, and I got 1 with pi out of that grouping right there. Next one I know is for r equals 2. 1 minus sine theta equals 2. That's my r equals 1 minus sine theta. I'm going to subtract 1 to the other side. And this is really asking when is sine theta equal to negative 1. And you guys know that we get to the lowest height on our unit circle of negative 1 when we're at 3 pi halves radians here. So there's only one solution, so I get a 2 and a 3 pi halves. So I'm going to extend this line down here since I think we should probably plot a few more. But I'm thinking I'm starting to see hopefully some sort of shape right here. So on my coordinate grid out here, and I'm still marking this with an x and a y because we're on a coordinate grid, but I am thinking of these in terms of r and theta. So thing number one, point number one that I know. R equals 0, theta equals pi halves. Well, the theta equals pi halves doesn't matter. The radius of 1 says we're 0 units away from the origin. So therefore, we're at the origin. Our next point says we are 1 unit away from the origin at an angle of 0 degrees, or 0 radians, I should say. So that point goes right here. We are also 1 unit from the origin at pi radians. So that point is going to go right here. You should notice that these are left-right symmetric of one another, those 2 points, and they had better well be because we proved that there's guaranteed to be left-right symmetry in this graph, and we're seeing it with those 2 points right there. Finally, we're getting to this radius of 2. We're 2 units away when we're at 3 pi halves, which we know is straight down. So it looks like that's about my measurement of 1 right there. So we should be getting to a measurement of 2 right down here. And what I think I should do just to like help people out with this is I'm going to label these points as A, B, C, D, just because I know graphing these can be hard. Here we're at location A, this was B, this is C, and this is D right here. So I'm seeing some of the points that are going to be on our graph, but it's really kind of not clear to me. Maybe I can help by like filling in some other points right here. So I'm thinking here we clearly hit our 0, pi halves, pi, and 3 pi halves. We hit our 4 axis angles right here. Maybe we can give ourselves like at least 4 other points at like our pi fourths, right? Maybe I can hit my like pi fourths, 3 pi fourths, and, or actually even better yet, here's what I'm going to do for myself. I'm going to be even smarter for myself right here. And here's what I'm thinking. Pi fourths is a nice clean angle, like it's 45 degrees, but pi fourths gives me outputs from the sine function of like root 2 over 2, and I don't want to have to estimate square root. So my question to you is, what angle in radians gives us the cleanest numbers out from the sine function that aren't the ones that we already checked? And I'm thinking I don't want my root 2 over 2s with my pi fourths. I don't want my root 3 over 2s. And I know the sine function measures height, so I'm thinking the root 3 over 2s are the 60 degrees is out there. So I'm thinking that the 30 degrees is are where my height is going to be just 1/2. That's going to be really easy for me to graph. So I'm thinking maybe let's check our pi sixths, 5 pi sixths, 7 pi sixths, and in fact, actually, oh my gosh, we don't even need to go that far. So listen, I'm talking big strategy stuff right here. So here's the thing. Our pi sixth and our 7 pi sixths, why would we check both? We know that we're going to get our left-right symmetry on this graph. So I don't know that I need to do that. So it seems like I could just check these 2 angles over here and see, and then mirror image them over with symmetry to get these 2 angles that are going to be over here. Because we've already proven that we're getting left-right symmetry on this graph up above. So let me just go ahead and check out just pi sixths and 11 pi sixths, which is the same as negative pi sixths. And let's see what we end up getting here. If I plug in pi sixths into this guy, I'm getting, so theta is pi 6, so r equals 1 minus sine of pi sixths. We know that pi 6 is 1/2, so r equals 1 minus 1/2, and so r should just be equal to just 1/2. Now for 11 pi sixths, we're going to get a little bit of a different thing here. R equals 1 minus sine of 11 pi sixths. Well, I know that 11 pi sixths on my unit circle is this guy that's down a little bit right there, right? So we're going to be getting the negative of that same value. So r equals 1 minus negative 1/2. That's really going to give me r equals 3/2 right there, right? So these are two new points that I know that are on this guy right here. So I should be able to travel 1/2 of a unit. So this is 1/2 of a unit right there out to the tick marks. I need to travel in 1/2 of a unit in the pi sixths direction. So I feel like that point is going to be there. And therefore, this point is also going to be there on the left side by symmetry. Similarly, I know that I want to go 3/2 units in the direction of 11 pi 6. So that might be like this guy over here. And similarly, we're going to get one that's going to be looking like this guy that's over here. So I'm thinking to myself, if I wanted to draw a curve that connected all of these points that we've graphed, and I guess I should go ahead, I'm gonna label some more points out here. A, B, C, D, let's call this E and F. This was my E, and this was my F, and I'm going to go ahead and call this E prime and F prime. Those are my symmetries. Then it seems to me like the curve that we're going to generate that's passing through all of these things seems to be doing something like this. I feel like I'm getting like some sort of heart-shaped graph out there based on the points that we just drew. And I want to comment over here, E prime and F prime, symmetric. Symmetry right there. So I feel like we're getting this vaguely heart-shaped graph right here. So now that we've done all this hard work on our own, let's go ask Desmos if Desmos agrees with the graph that we've drawn. And before I do that, I guess I want to talk strategy big time here. The strategy that's going on here is I want to pick the easiest possible numbers. So again, I picked things like saying like, oh, when do we get whole numbers for R? What are the convenient angles? What's the nicest angles there are to plug in for me here? I know that like nobody thinks of 11 pi sixths being a nice angle, but it is if you know that you're going to plug it into a sine function to get out 1/2. Are there nicer numbers that we get out from trig functions? Not really. We got our ones, our zeros, our negative ones, and then I needed some more, so I went for the halves. I avoided my root 3 over 2's, and I avoided my root 2 over 2's. Plug in nice numbers into your equation so that you get out nice numbers. I mean, that's what reasonable people do for themselves when they're trying to graph something by hand. So do yourself those favors. So we want to go to Desmos now and see, did we get the right graph for r equals 1 minus sine theta? And when I pop over here and do this, r equals 1 minus sine theta, r equals 1 minus sine of theta. And oh man, I feel really, really, really good about the thing that we just drew right there. Let's do our little back and forth here. Okay, so it should be more circular shaped than I drew it, but damn, we nailed the structure of this thing in a big way right here. That was pretty, we did a very good job of identifying enough relevant points to get a very good shape out there on the graph. We can see we did go down to a height down here of -2. I think probably the most confusing thing about this graph to me is it's not super clear what this graph's supposed to look like at the origin. If it's supposed to like come in here and like be a curvy thing down there or be really steep right there. This is this topic that you're going to explore in calculus. In fact, I will go so far as to say, literally today, I made a video for my Calculus 2 students where we discussed the fact that we know that this is going to be a very, very sharp point that we're actually arriving at this little 0, 0 origin right here. In fact, I'd go so far as to say the steepness of the curve at 0 is that we are infinitely steep right there. Right? Which is a little bit weird. That's a calculus feature. And I literally used this graph in my Calc 2 class today, and we explored the graph, and the question that we asked in Calc 2 was, where are all the locations on this graph where a straight line that touches this graph would be vertical? And what we can see is that here at this edge over here and at this side edge over here are two locations, but that this origin point is actually a third location where we would get what we would call a vertical tangent line, where the steepness of the graph is straight up and down right there. I literally did that in a video today for my Calc 2 students, so this stuff is is directly applied in our later calculus courses out here. So that's good to know. So basically, I think we nailed this graph right here. Super good job. If you're graphing trig equations by hand, it takes a little bit of work, but making this table of values is definitely the way to go. But you got to strategize. Pick the smartest values that you can pick for yourselves. Make these kind of statements for yourself. I know that the sine function spans from -1 to 1. Therefore, we should get out radii that look like blank. Say statements like that to yourself. It's really, really helpful. So, in general, these graphs, these types of graphs that we're looking at have a name. They're called cardioids, and you should recognize the name cardioid by its like cardio, cardiac. It's these things that are heart related. This is a heart-shaped curve that passes through 0, 0, and they always have this structure right here. You can see that we just had this graph where a was equal to 1 in this case right here. Let's go ahead and check out a couple more of these other options of things that might crop up in Desmos right here. So if I make this a little bit more generic, then you should see the two things I want to do are say 1, r is equal to 1 plus sine of theta. So you should notice that if I swapped our minus to a plus, we're just getting the cardioid from the top instead of a cardioid from the bottom. What happens if we switch for sine and switch sine out for cosine? So again, it's one of those things where I want you guys to think mathematically, and I'm asking you to not do a bunch of work. I'm just asking you to think. The sine function just gave us cardioids that were top and bottom opposites of one another with the positive and the negative. So what should the cosine function do? Well, we know the sine function is a measurement of height, and by swapping out positive sign for negative sign, we got opposite heights. The cosine function, we should be thinking measures width. So I'm anticipating when I swap sines for cosines here, I'm going to get two side-by-side cardioids, basically the 90-degree rotation of this image that we're looking at here. Oh, and what do you know? We get a cardioid laying on its side right here. So this matches all my trig intuition that says cosine makes left-right things, sine makes top-bottom things right there. The only other thing that we saw was that in our general form that I stated, there was parentheses here and a factor of a. So I can add a slider for a, and what we're going to see happens when we do this is that a just tells us, are we going to have a tiny one, or are we going to have a big one out here? And you can see the butt of the cardioid is growing right here. Yeah, the factor of a just sort of shrinks or decays us in size. You can see here things like when a is 5, you can see the total span goes from 0 to 10 on the x-axis right there. So it looks like the cardioids are always stretching twice their span on their given axis. Cosine references x-axis, sine references y-axis. So we can see some generalizations that we can make about what this parameter a is controlling graphically for us there. Let's go ahead and look at some other generic, we're going to look at another example right now and then look at some other general forms that we see. So let's look at this example here. The following equation seems similar to the previous. The previous was 1 minus sine of theta equals r. This is 3 plus 2 cosine theta equals r. So it seems similar because we have a constant plus or minus a constant times a trig function equals r. So this has very, very similar structure. How is this going to be a little bit different? And this is a really good time for you to not open Desmos and stop and think for yourself and press pause right now on this video and say, what do I think is going to be the same? What do I think is going to be different? And you should specifically play some of these strategizing games we played right here. I'm not saying make a table of values. I'm just saying, like, even just play this game right here. What kind of radii will we see? So, now that you've not gone to Desmos, you've played around it by yourself, and you've paused and unpaused the video. A thing that I'm thinking to myself here is cosine takes on values that span from -1 to +1. So at its most extreme lower value of -1, we're going to get 3 minus 2, which is an r value of 1. At cosine's most extreme positive value, we're going to get outputs of +1, and 3 plus 2 is 5. So it seems like because, so I'm going to even, in fact, do a little bit of math like this here. Check this out. Cosine of theta lives between -1 and 1. If I multiply all three sides of this inequality by 2, then we get 2 cosine theta. Spans from -2 to 2. And now if I add 3 to all three sides, I get that 3 plus 2 cosine theta is between 1 and 5. And I'm noticing that 3 plus 2 cosine theta is exactly r. So I'm noticing things like radius is never 0. So therefore, it never passes through the origin. Which, specifically, cardioids are always, the reason why this a is factored out front is because as long as the coefficient in front of sine is the same as the constant right here, then they're going to pass through the origin. This one does not have that going on. The 2 is different than the 3, so it's not necessarily the case that it's going to pass through the origin right there. So just some little bits of manipulation like this can help you identify features of the graph. Actually graphing them is always going to take like a whole bunch of work right here, but maybe we can get by with like a little bit less of saying things like, I expect this graph to be like a cardioid, but I expect it to be laying on its side. And I also want to say here, because cosine, I expect a cardioid-ish shape laying on its side. Not passing through the 0, 0. So I'm going to go graph it, and I expect to see two things. One, I expect to see basically like our old graph, except not touching 0, 0. And I expect it to be the laying on the side version because we're referencing cosine, which is going to give us more of a left-right interaction than a top-bottom interaction. And I expect it to miss 0, 0, and I know that to happen because I started with an inequality that is just a basic definition, a baseline property of cosine, and I modified this inequality to make it look like our equation of interest so I could identify relevant features of r rather than of cosine of theta here. So let's go ahead and see if this is true. R equals 3 plus 2 cosine theta. R equals 3. R equals 3 plus 2 cosine theta. And what do you know? We got a cardioid-like shape. It's not going through the origin. It's laying on its side, right? So we can make these general classifications about these here. And this is really weird. This is like a circle that's like almost like a circle. It's like a circle where somebody just like poked it as hard as they could with their finger and it shifted it and it dented it, right? There's an interesting shape right here. Now, maybe what we should then say to ourselves is, what are all the things that might happen when you have equations that are of this structure right here? So if we come back, so by the way, we nailed it with the properties that we identified here at least. It's like a cardioid, but not quite. It's going to be laying on its side because it's cosine instead of sine, and it's not going to pass through the origin by doing a little bit of algebra right there. So what types of shapes might we end up saying? Oh wait, did I not grab the? Okay, that's fine. That's fine. Let's generalize this and put an A and a B in that location right there and see what we can see. So I'm just going to make this an A and a B over here in Desmos, right? A plus B cosine theta. I'm going to say, yeah, go ahead and add a slider for all those things, and let's play around with these shapes and see what we see. Notice that this looks like basically almost exactly like the shape that we just had. In fact, this is even in the same proportions. We had 3 and 2. Here's 1.5 and 1, so we're same proportions, just a shrunk down size. So what happens if I make B bigger? Ooh, it looks like this generated an inner loop right here. Now, my question to you would be, under what conditions does this equation have an inner loop? And maybe you can kind of answer that here. What needs to happen for this to have an inner loop? Well, it seems to me like the B value needs to be more extreme than the A value right here. Notice that B is bigger than A, we have a loop. B is equal to A, and we're touching, there's the perfect cardioid, and B is less than A, and we just get sort of the rounded edge version of it right here. Notice that this even makes sense for us to have negative B values and negative A values, and in which case, ooh, we can see that the inner loop swaps out to be the outer loop as we transition our A values through 0. That's really interesting. The inner loop and outer loop swap roles, and then it disappears as it becomes more extreme than B. So making these types of generic classifications of these things, what's really hard here is it's hard for me to graph any one of these individually. What I don't want to do is make 14 different graphs to represent all the different possible conditions, but it seems to me like it's pretty easy for me to write a sentence or two that relates what A and B do to the shape that we're going to end up seeing right here. And that's what I really like us to be able to do for a lot of these harder graphs. So That's where we're going here for the remainder of this video. We've seen cardioids. What other shapes might we see? Well, here's a shape. It's called a limacon. This is one of those French words with the French little lettering down there, where if you guys know French, this C actually gets that little like squiggle that's down there underneath it right there. It's a French word for snail. Let's go ahead and take a look at what these graphs are going to look like. Oh, wait, these are the ones that we just did, right? Okay, so this is a limacon right here. A plus or minus B sine theta. We just did those right there. And so I think we can say things like, no inner loop if, and now let's go back and ask ourselves, when was it that we had no inner loop? It looks like it's when the A value is more extreme than the B value, right? And we can verify that over here. A is more extreme than B, no inner loop. So A is further from 0 than B, no inner loop. If A is further from 0 than B, inner loop if B is further from 0 than A. And inner and outer loops swap roles as A passes through 0. I think that's a pretty good generalization of the shapes that we're seeing right here. I think I should say mostly look like cardioids, but only hit 0, 0 if A equals B. So there we go. There's our generalizations of our limacons right there, and we just explored those in Desmos to find these kind of general statements about them. We play the same game with the next one. These next ones right here are called lemniscats. It's a Greek word for ribbon. Let's go ahead and throw these graphs in there and see what we end up seeing. See if we can make some generalizations. This is the last one that I'm going to generalize. You are going to generalize the remaining two for homework. So I think it's valuable for you to see the types of statements I'm saying now, so that you can see that roses and spirals are your homework questions to make a few sentence generalizations about what the parameters control. So let's do lemniscats together here, and then you'll see your homework question. So for our lemniscats, I want to graph r squared equals a squared sine of n theta. Got some sliders. Now, what you're going to see here, now I've typed this in here, is that Desmos is annoyed by something. What's bothering Desmos today? Well, here's the thing. If I hover over it, it's going to tell me polar equations must be linear in R. Linear meaning you can only have a single R. R squared is quadratic, not linear. So it's bothered by the fact that there's a square on this R right here. And what I'm thinking to myself is, it's probably the case that Desmos is doing some numerical computation to produce these graphs under the hood, and it can't do them if that squared is in there. So what I'm thinking to myself is this. If I want to still graph things of this general form, I can just take a square root on both sides, but what do you need to always do algebraically if you square root both sides of the equation? Is introduce a plus or minus. So what I'm going to go ahead and do here is I'm going to copy this. Ooh, sorry, I'm not going to do that yet because I know what it's going to do to me right now. When I do square root, oh, okay, all right. I can cut and paste this underneath the square root. I can get rid of the square now, and now I've got part of a shape. And now I'm going to take this whole dang thing and copy it and make that my new expression that's right here. But I'm going to make this a negative so that we can see that we do get both the top and the bottom from doing this. You can see that this depends on both A and N. So I've got sliders for A and for N, and I'm going to zoom in a little bit. So my first question is, what's A doing for us? Well, it seems like A is just sort of like a scaling factor that makes us bigger or smaller. Notice that A being 1 takes us from 0, 0 up to 0, 1 right there. So it seems to be sort of measurement. It's not like a radius term necessarily, but it seems to be giving us this sense of measurement of like the maximum span of the graph out there, right? And if I go to A being 3, then we can certainly see that we're hitting 3 right there as our max and our min right there. So describing A doesn't seem to be too terribly difficult here. What about N? What's N doing? All right, are you ready for this? Are you ready for this? What's N doing here? Oh gosh, that's not what I expected to see. Oh my gosh, now what a freaking cool shape that is, but holy cow. So what's happening here? So simple, complicated, more complicated, Uh, maybe cleaning itself up. Oh no, more complicated, more complicated. But what's happening is, ooh, oh my gosh, oh my gosh. Okay, bunch of weird stuff just happened there. So we started with n equals 1, and we saw 2 lumps. Now I see n equals 2, and I see 2 lumps. But there's a bunch of crazy stuff that happened in between. Let's see what happens if we go bigger. Here's going between 2 and 3. Oh my gosh, we're getting all these awesome like flowery patterns out here. But what I'm noticing is that as we get really close again, oh, ooh, now this is interesting. Now I'm getting, with n equals 3, I'm getting 6 petals on my flower here. So if I go to n equals 4, I'm only getting 4. So if I go to n equals 5, I'm getting 10. What generalization can you make about n? Well, one thing I think I can say about n is I would like to only look at whole number values of n, at least for right now. So I'm going to make my step size 1, so it doesn't ever give me those decimal values in between. Now looking at this, I can see with n equals 1, I'm getting a total of 2 petals. N equals 1 gives 2 petals. N equals 2 gives 2 petals. N equals 3 gives 6 petals. N equals 4 gives 4 petals. 5 gives 10 petals. 6 gives 6 petals. 7 gives 14 petals. 8 gives 8 petals. 9 is going to give 1, 2, 3, 4, 5, 6, 7, 8, 9, and another 9 makes 18. So it seems to me like A is controlling the maximum radius, the maximum possible radius right here. And you should notice that makes sense because we're looking at A. A could be a popped out of the square. It's just an A sitting out front. Sine is going to go from 1 to -1. And so this A is going to be the biggest that it could ever be, right? When it's at 1, it's just going to be A. When sine of this gives 1, square root of 1 is 1, and r is going to be equal to a. So a is the maximum radius. So, oh, sorry, I'm sitting over here typing. So what I'm saying here is what generalizations can we make about lemniscates with respect to the parameters a and n? It seems like our parameter a told us the maximum radius or the maximum distance from 0 that it would ever go. It looks like n was telling us, as if we view n as an integer only now, n was doing some crazy things for those small fractional values between whole numbers out there. As an integer, it tells us how many petals the flower is going to have. If n is even, the thing that I was seeing was if n is even, then we're getting n is 2 gives 2 loops, n is 4 gives 4 loops, n is 6 gives 6 loops, n is 8 gives 8 loops. So if n is even, then n is the number of loops. Alternatively here, if n was odd, we saw something different going on here. When n was odd over here, we were dragging the slider around and we started at 1, and at 1 there was 2 loops. At 3 there was 6 loops. At 5 there were 10 loops. So it seems like for our odd values of n, there actually ended up being twice as many petals on that flower, right? Which is kind of interesting right there. Not something you would ever be able to easily see by just looking at this equation. All right. So this is good. So we can. So this is basically me saying to you, if I give you the general form of a polar, of a polar graph, could you go play around with it in Desmos and add some sliders and describe to me what you're seeing? So what I'm not going to do is I'm not going to do these next two. The remaining two general shapes that are the pretty typical ones for people to see when they're first learning polar graphs are roses and spirals. You can see these have general forms just like our other general forms. They're all parameterized by like letters A's, B's, N's, stuff like that. By the way, Anytime in math you see a letter N, that's usually a hint that it doesn't just mean any number, it usually always means integers for N. N is our counting numbers. Whereas A's and B's are usually the pick anything you want for these. So you should notice that the rows has an A, so it's a sort of pick anything you want number, but that N is sort of a hint to you that you maybe only want to look at whole number values for N, but that's for you to decide. If you can generalize what's going on with N more generally than that, then great. On your homework questions this week, on your written homework, I'm going to ask you to answer these two questions. Make some generalizations like the generalization we made for lemniscate, like the generalization that we made for the lemicon. These aren't this. I'm not saying write me some big old paragraphs, but like list a few sentences that describe to me what A and what N are doing, what A and what B are doing, what features do they control in this graph. By the way, for the spirals, and I'll throw this hint in the homework, this one is really hard to see if you pick big B values. When I say big, I mean even like 2 and 3. You should pick B values like 0.01 and 0.02 and maybe some negatives in there as well, but pick tiny B values. It'll just make your graphs easier to see in Desmos. When this one, e to the power of, gets big real quick, and so it sometimes helps to make your B values a little bit smaller out there. So you'll see these two crop up in your homework questions. And so as my concluding statement here is, you should notice that our interest and concern associated with these graphs is different than what you're used to. The year is no longer 1970. I really don't care if you memorize these general forms, and I don't even care that much that you can graph these by hand. You should be able to, but it's not like I'm going to ask you to do 12 by hand graphs and show them to me with specific points on them. The year is now 2021. What I care about is that you are able to explore a mathematical topic that you have not seen before and form generalizations about what you're seeing by utilizing technology and your mathematical intuition. Right? So recognize that the doing is sort of the old-timey thing here, and the exploring is the more modern version. What does the graph look like is a boring question. How does the parameter of A control the shape of this graph is the more interesting question. Why do we get different graphs when B is positive versus negative is a more interesting question. So I want you guys to recognize that we are at like a period of time in history where we're directly acknowledging this transition away from questions like what, which are boring, and towards questions like why and how, which are interesting and which still require a human to think through. A computer can answer the question, what does the graph look like? Therefore, that's no longer a meaningful college level question anymore. What's more interesting is how would you determine that that's what the graph looks like? Why did that parameter control that certain feature the way that it did? How do I know that 3 plus 2 cosine theta isn't going to pass through 0? These are the interesting questions that still require human consideration. Therefore, these are the ones that are of interest to me. So this isn't so much about by hand graphing. This is more about me saying, hey, here's a general thing you've never seen before. Use technology and your mathematical intuition to tell me everything I need to know about shapes that are of this structure right here. That's the current modern question that we're more interested in here. So that's where I'm going to leave you for section 9.2. Where we're headed in our next section coming up right here. Oh, I'm realizing I've got my lecture info ever so slightly wrong right here. I didn't change my section title. This is section 9.3. There we go. I get it right for the last 1 minute of the video right here. Polar. Oh wait. No, that's today. No, I had that right. 9.2 was today. I was meaning to change section. This is 9.3. We are going to look at complex numbers in the complex plane, as well as de Moivre's theorem. That's a moi. That's a French dude right there, de Moivre's theorem. And I will tell you, this is a more of an explorative section that we did here today. De Moivre's theorem is going to finally take us back into, we're going to be like actually like doing some math. That's not going to be the easiest math that we've done all semester. De Moivre's theorem gets a little bit complicated. It's not too terrible, but I'm just saying, like, we're going to be doing some real algebra and some real solving for the De Moivre's theorem stuff, paying real close attention to the calculations that we're doing. This has been more of a conceptual and a graphical section here of this chapter so far. De Moivre's theorem is going to bring us back to the computation end of things. That's where we're going to start next week, is with De Moivre's theorem and complex numbers, square roots of negative numbers. Imaginary or complex numbers is what they're called. Those are terrible names. They are not imaginary as in made up. They are not complex as in complicated. The guy who originally kind of defined these numbers got really upset at everybody else that named them those things, and he like spent half of his career like trying to get the names changed, and they stuck anyway. And and he was pissed about it. So I agree with him. They're not imaginary or complex, but those are the names that we now affiliate with those numbers there. So that's what we'll be looking at to the start of next week. I will see you guys in week 13 with complex plane and de Moivre's theorem. Have a good one, everybody.